I'm calling this lecture Plotting Sequences because I want to show you a technique that's often very useful when you're studying a sequence of numbers. And that is, well, to make a picture of it, or as we say, make a plot. So I'll show you what this is about by showing you various examples. Let's consider a sequence that we did once before. This was a sequence in which you either had to divide a term by 2 to get the next term, or else multiply it by 3 and add 1. We don't really need to remember the details of that because I'm just going to show you the first few terms. It starts out with 3 and then 10 and 5, 16, 8, 4, 2, 1. And then as we saw, it actually starts to repeat 4, 2, 1, 4, 2, 1 forever. Now we can just plot this as I've shown you down below. So you see above the number 1, I show you a point at height 3 to indicate that the first term is 3. And then above 2, I show you the second term is 10. So you can see 3, I go up to 10, then down to 5, then up to 16. And there is the plot. And you can see the fact that we have this repeating or periodic behavior by the fact that we see this same zigzag pattern repeating itself, and that would continue however far we took this to the right. So we can also say the following. We can say that at the beginning there's transient behavior. If we think of this as a series in time, if we think of the numbers at the bottom as time 1, time 2, and so on. So we see some initial transient behavior, but eventually the long-term behavior of this sequence is that it becomes periodic with period 3. Here's another example. Here I've plotted the terms of a geometric sequence starting with 1 and then using r equals 1.5, so I get 1.5 from my next term, then 2.25, 3.375. Now looking at the scale that I've chosen, and I've chosen a scale so that you can actually see what happens in the first 20 terms, you'll see that at the beginning it's indistinguishable from 0. Those numbers are so small on this scale that you can't really see anything going on. But eventually you see that we're forming this interesting sort of curve that's suddenly going upward, spiking upward there. This is what a plot of a geometric sequence will often look like. All right, let's go on and do the Fibonacci sequence. So I've plotted the numbers 1, 1, 2, 3, 5, and so on, all as heights. Of course, at the beginning of the sequence, again, the numbers are so small at the scale that I'm showing you that you can't really see that they're non-zero. But eventually we see, again, this same sort of behavior. The points are getting higher and higher, and then discernibly higher and higher as we go to the right. And maybe the most remarkable thing is when you look at this picture, I hope you say to yourself, well, it looks just like that picture, right? These two pictures look very similar. And so we've discovered something interesting that I think we may never have discovered if we hadn't actually had this idea of plotting the sequence. Namely, there seems to be a great deal of resemblance between the Fibonacci sequence and a geometric sequence. Now, the Fibonacci sequence is not a geometric sequence. And how do I know that? Well, if you have a geometric sequence and you compute the ratio of successive terms, so what you get by dividing one term by the previous term, you will always get the same number, no matter where in the sequence you do that. So for example, if you take this sequence that begins 1, 1.5, 2.25, and so on, and calculate 1.5 divided by 1, and then 2.25 divided by 1.5, and then 3.375 divided by 2.25, you're always going to get that number r, the common ratio. And that has to happen because of the way that you made the sequence. So in a geometric sequence, the ratio of successive terms is always the same number. All right, so could the Fibonacci sequence be a geometric sequence? Well, we could test it in this way. Let's calculate the ratio of successive Fibonacci numbers. So I have done that, and I'm showing you the results in a table. So I can start that with n equals 2, that is to say I can calculate fn divided by fn minus 1, and that's 1 divided by 1, which is the number 1. But if I try it with the next pair of terms, if I try it with the second Fibonacci number, f2, and the third Fibonacci number, f3, well, that is 2 divided by 1, and that's not 1, it's 2. Now, as soon as you've done that, you can see that this is not a geometric sequence. It's not a geometric sequence. So you may wonder, why did I bother to continue this calculation any further? If I was just trying to see whether or not this was a geometric sequence, I already saw that by my first two computations. However, let me be persistent, or maybe crazy, and let me just continue these same calculations. So I've divided 2 by 1, now let's divide 3 by 2. Well, that's different from both previous answers. It's not 1, it's not 2, but it's halfway in between. It's 1.5. And then if I divide the next Fibonacci number, 5, by 3, I get yet another number, 1.6667 approximately. So in every case, I'm calculating a quotient of 2 whole numbers because all the Fibonacci numbers are whole numbers. But to compare them, I'm converting them into decimal approximations. And as you look further and further down this list of calculations, you may be somewhat surprised. It's something you observe here. And this is, in fact, why I was persistent in continuing to do this calculation. I actually knew that this was going to emerge. And what is it that we're seeing? How would we describe what we're seeing here? Well, it seems that as you do this calculation over and over again for increasingly large values of n, that is to say further and further along in the Fibonacci sequence, these ratios aren't exhibiting random or behavior that they're jumping all over the place. It seems as if they are settling down to some value, and that value looks to be about 1.618. That's pretty remarkable. The ratios seem to approach a mysterious value. Not any familiar looking number, I don't think. It's a number somewhere around 1.618. Now, of course, all of this is based on just a little bit of numerical evidence. We've only used the first 14 terms of the Fibonacci sequence. Maybe what we're seeing here would fade away or go away if we continue the calculation further. So one thing you might ask is, does this really happen? In other words, is there really some value that's being approached by these ratios of consecutive Fibonacci numbers? And then another question you might ask right on the heels of that is, well, if there is, what is this number? What is this crazy, mysterious number? Now, I really can't answer the first question satisfactorily, but I can eventually answer the second one. Before I do that, however, I've already jumped ahead to looking at a different sequence. I'm now looking at the Lucas sequence. So remember that the Lucas sequence is very similar in the way it's formed to the Fibonacci sequence. In both cases, once you've given yourself 2 starting values, then you simply add successive terms to get the next term. The only difference between the 2 sequences is what pair of numbers you begin with. In the Fibonacci sequence, you begin with a pair of 1s. In the Lucas sequence, you begin with a 1 and a 3. So I've taken the Lucas numbers, which are 1, 3, 4, 7, 11, 18, 29, and now I've done the same calculation with them that I did with the Fibonacci numbers. Namely, I've computed the ratio of the nth Lucas number to the n minus first Lucas number. I calculated 3 divided by 1, 4 divided by 3, 7 divided by 4, 11 divided by 7, and so on. And the numbers I'm getting are not the same as the ones I saw for the Fibonacci sequence, which I'm showing you again. Instead of starting with 1 and 2, I start with 3 and 4/3, which is about 1.3333. So they're different numbers. However, remarkably enough, as you continue the calculation in the same way, as you can see by moving further and further down that right column, it seems that again the ratios are approaching a value, and not only that, they seem to approach the same value as the one we saw for the Fibonacci sequence. So it's pretty remarkable. And again, we can ask that pair of questions. Is what we're seeing here, is it really happening? It seems pretty likely, doesn't it? The other question is, what's the number? What are we approaching? Now, both of these sequences, the Fibonacci sequence and the Lucas sequence, use the same sort of recursive formula in their definition. Pn equals Pn minus 2 plus Pn minus 1. That is to say, in both cases, you compute a term of the sequence by adding the two previous terms. Now, let's call a sequence that uses this sort of recursive formula a Fibonacci type sequence. We've just had two examples, the Fibonacci sequence and the Lucas sequence, but you can make up your own example. Just pick two positive numbers to begin, and then generate the sequence. And here's what I claim. Again, you will find that the ratio of successive terms, that is to say Pn divided by Pn minus 1, will approach this same mysterious value, 1.618. Now, I can't completely explain why this happens. That would require more advanced concepts in calculus and analysis. But I can show you where the number comes from, and that's what I'm going to do next. Now, I want to be guided by the following heuristic, by which I mean a statement that's not completely precise or logical, but suggestive. And the heuristic statement is, looking at what we've seen in our calculations, these sequences aren't geometric sequences. We know they're not, but somehow they want to turn into geometric sequences. That is to say, as we go further along in the sequence, they look increasingly like geometric sequences. Now, obviously, this is a heuristic kind of statement. These sequences don't have any willpower or thoughts and don't want to do anything at all. Nevertheless, it's helpful for us in our thinking to think, they're trying to become like geometric sequences. And that leads us to ask, in fact, a question that is quite precise. Namely, is it possible to find a sequence which is of both types? That is to say, is there a sequence which is both a Fibonacci type and a geometric sequence? In other words, is there a sequence which has the recursive formula that we have in the Fibonacci type sequences, but also is generated in the same way as a geometric sequence? It is a geometric sequence. And the answer to this question is yes. We're going to look at an explicit example. In fact, there's a little bit of choice in giving the example. It turns out that I can just take the first term in the sequence to be the number 1. Now, the second term, actually, I don't have that freedom. I'm going to call the second term x. And later on, I'm going to figure out what value I want to use for x. But I want to give an example of a sequence. It will be a sequence of Fibonacci type. It will also be a geometric sequence, and it will begin with the number 1 and then another number, which I'm now calling x. All right, so here are two columns showing you how I think about this sequence in two different ways. So on the left, I'm thinking it's supposed to be a Fibonacci type. Now, the first two terms, as I've already said, are 1 and x. And how do I get the third term? Well, since it's supposed to be a Fibonacci type sequence, I need to add 1 and x. So I get 1 plus x. Now, how do I get the next term? Well, I have to add x and 1 plus x. And using our algebra, that gives us 1 plus 2x. And then adding 1 plus x and 1 plus 2x, I get 2 plus 3x. And then next is 3 plus 5x, and so on. All right, so that's how the sequence goes, except that eventually I want to figure out what to use for x. Looking over on the right, I want again to start with a 1 and an x, but now I'd like to think, well, it's supposed to be a geometric sequence. So that means I'm always multiplying by some common ratio, and it has to be x, right? How do I get from 1 to x? I multiply by x. So if I've done that once, I must do it again to get to the next term, which will be x times x, which we all know that we should write as x squared. And then when you multiply by x again, you get x cubed. and then you get x to the fourth, x to the fifth, and so on. Okay? So what we've written looks very different from what we wrote over on the left, right? On the left, we say the sequence begins 1x, 1 plus x, 1 plus 2x. On the right, we say it begins 1x, x squared, x cubed. I would like, however, for these two sequences to be the same sequence. Now, how can I make that happen? Well, they already agree in the first two terms. The first place where they seem like they might disagree is the third term. And I make them agree. You see, I want it to be 1 plus x, but I also want it to be x squared. So what I'm demanding is that 1 plus x equal x squared. So out of all this thinking about the two types of sequences, I've come up with an equation. It says 1 plus x equals x squared, and I'm going to use that equation to determine the number that I want to use. All right, here's that equation again. 1 plus x equals x squared. Now, you have already had a course in algebra where you learned how to solve equations of this type. Since there's an exponent of 2 on the right, we say that this is a quadratic equation. This is an equation of degree 2. And in an elementary algebra course, one learns all about solving quadratic equations. Now, you may have learned how to solve quadratic equations by factoring, but that only works in certain circumstances, and in particular, it doesn't work on this one. This is not one that can be solved by factoring. What you need to do is to rewrite the equation with all the terms on one side and then apply something called the quadratic formula. Okay, well, I hope you remember it, but let me just say it aloud. The quadratic formula says that x equals minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. I hope that has a familiar ring. Of course, I've used letters A, B, and C. What do they stand for? Well, they're the coefficients in the equation. So in our particular equation, when you write it with all the terms on one side, A is 1, B is negative 1, and C is negative 1. So you can just plug those numbers in, and you come up with what I'm showing you in the box there, namely x is 1 plus or minus square root of 5 divided by 2. Well, I didn't quite say what was in the box, did I? I said plus or minus. In the quadratic formula, there is a plus or minus sign. In the box, I've chosen to use the plus sign because if I take the negative sign, I'll get a negative number. And I don't want an example like that. I want to take an example in which I get a positive value for x. So there really is only one positive solution to this equation, and there it is. X is 1 plus square root of 5 divided by 2. Pull out your calculator if you like, or just trust me that in fact its value is about 1.618034. In fact, that's accurate to the last place that I've shown. It's just been rounded off in that last place. And that's the number that we were seeing in all those previous examples, okay? In the example involving the Fibonacci sequence and in the example involving the Lucas sequence. And if you tried it on your own with your own choice, you saw that number too. Okay, so this number is kind of interesting. It comes up in many different disguises in mathematics. It's called the golden ratio. By definition, what is it? It's 1 plus square root of 5 divided by 2, that number up above. Now, it comes up often enough that, in fact, there's a standard Greek letter that we use to refer to it. It's the Greek letter phi. And an awful lot has been written about this number, the golden ratio, some of it mathematical, some of it kind of fanciful, theories about how this number happens to come up in all sorts of areas such as architecture or music and so on. Some of it begins to get a little bit silly. But honestly, it is an important number, and in particular, it shows up when you're studying something like Fibonacci sequence or related sequences.